All right, here's where we left off last time. We left off talking about dictionaries. Well, really, I didn't even get to dictionaries. That's where I stopped. But I gave a little bit of a hint that they kind of appear like they're lists, but there's a little more magic to them under the hood. We're not going to go into all the details of how they work under the hood. It's a little complicated, but there's a little bit more special stuff going on with dictionaries. You could look at them and say, like, okay, well, they're like lists, but you can index them with things like strings instead of just integers. There's other things you can index them with as well, but strings are a simple example. So here's an example of creating an empty dictionary. You use the braces, the squiggles, all right? You use braces. You can add new things by just saying, okay, some dictionary at, like, Billy, 74, right? You might say, like, well, Billy doesn't exist. Well, this is what creates it, all right? Sally, Jimmy Bob, whatever, and then I can print it out. And you would see something that looks like this. In fact, let's do it for fun. Bless you. Right, there we go, cool. All right, by the way, you could also create a dictionary in line like this, right? You could, that's how you would do it if you didn't want to, like, add them individually, but whatever. So there we go, cool. You could also, like, so if I run this, we see the output. I could also, like, index it now at Billy. And what do you think I'll get? 74, right? What about Sam? What do you think I'll get? Key error. Doesn't exist. And you look at this and you go like, okay, yeah, I never assigned anything to Sam. Now if I were to go here and say, whoops, what the heck? Well, now it will work, right? Sam's crushing the course. So, in the example, the dictionary was created with 3 unique values. I added another one for Sam. Oh, my goodness. What is going on? Stop it. There, now we got rid of Sam. Cool. Awesome. Now, the keys are what we call the things we index with, right? That's why we saw that key error. Sam didn't exist, so it said key error, Sam. So the keys are what we use to index the dictionary. Also, by the way, dictionaries are sometimes called maps or key value pairs, but they're all the same thing. The key is what we use to index, and they must be unique, obviously, right? Like I can't say like the key must be unique, should be kind of obvious, right? Because if I were to go like, okay, no, 78, well, it's just going to overwrite Sally's thing. Assuming these are like grades, let's say. We're going to overwrite Sally's grade with 78. Okay, do you see what I mean? Like keys have to be unique, and it should be kind of obvious why. Because, well, that would just overwrite what it was if we use the same key. But the values do not need to be unique. They're entirely independent. Right? The values can be whatever we want, but the keys must be unique. Oops. And then, yeah, okay, you can index the dictionary at individual things, like Jimmy Bob was 99 and Sally was 88, for example. Okay? Cool. If you want to update the value at a specific key, well, that was like what I just did, right? Sally is 99, right? Sally did really well on the test. I don't know. So, cool. Cool, right? Any questions about dictionaries? You can kind of see that, like, you can index the dictionaries kind of like how you index a list, where the list at some index is a value, right? But what's interesting about dictionaries is, like, unlike a list, there's like an orderedness to a list, right? Dictionaries don't really have that, right? If I have a list of size 10, there's indexes 0 through 9, right? And like, what comes after 0? 1. What comes after 1? 2, right? When you look at this, you're like, what comes after Sally? I don't know. It's not really, is it alphabetical? Maybe if we could sort alphabetically, but there's no like implicit, there's no explicit, at least, ordering to dictionaries, which is kind of interesting, right? So any questions about what you're seeing here? Now at this stage, their amazingness actually doesn't stem from this cool feature. This is a cool feature. You can basically make like a list type thing, but you index it with whatever the hell you want, which is pretty cool. That's cool in and of itself, but what makes them so good is a whole other thing. So imagine I had this, okay? Right? Or maybe I should even make these, well, really I probably should have made them, no, they're fine, right? So imagine I have this. This is not a dictionary. This is a list of lists that contain a pair of information, Billy and their grade, okay? Do you see kind of like how it's trying to achieve the same thing as the dictionary? Do you kind of see what I mean? Where the dictionary, like this was the key, and that's its associated value. So you've got pairs of information. But here, like, okay, an index 0 is Billy at 74. Index 1 is Sally, 88, right? Right? So we've got the big list, which is every student, let's say, and the individual lists are always going to be size 2, which is going to be their name and their grade. Okay? Okay? Any questions about what we've got? So, if I were to say, well, what is some individual student's grade? How do I find it? Well, I'm going to have to do a linear search, right? In fact, let's write that real quick. Def find student grade. Student's name. All right, for if student at index 0 is equal to name, we found it. Return student at index 1. Otherwise, return, I don't know, -1 or something, right? Cool. I think that should work. Right, so what is this linear search doing? Well, it's the same linear search as everything we've done before, but with a little bit of a twist, I suppose, in that students is the collection of things, right? But before, when we were doing linear searches, we'd have like a list of integers, for example, where now we have a list of lists, right? And in those lists, I have, so for each student in students, right? So that'll do Billy 74, Sally 88, Jimmy Bob 99, right? Right? Yeah? But how do I compare the names? Well, I have to say student at index 0. That'd be, oh, their name, right? And if it's the same as what I'm looking for, I'm going to return student at 1, its corresponding grade. Do you see? I'm seeing a lot of blank faces right now, so it's very difficult for me to tell if this makes sense. And if this, what I'm trying to do here doesn't make sense, I can't move on to the next thing. Does this make, question, any thoughts, concerns, questions, or anything? Remember, if you have a question, half the room probably has the same question, so ask now, please. It's a linear search, but the things in the collection of things are lists that we need to index. Like the student at 0 is the name, and then what do I actually want to return? The value is so, like the grade associated with the name. Okay? Yeah? Yeah?
Why are you returning -1 again?
That's just like, oh, if I couldn't find anything, return negative. It's a sentinel value. Okay. It means that like if I ever call this function and I get back a -1, it means that the student's not there.
Could you return none?
You could. There's nothing wrong with that, but here's why you maybe shouldn't. Because this function, here, should return an integer, right? And then if you return none, like, well, none, it's not an integer, right? So to make it like type consistent, you could argue with me saying like, well, look, you are returning a sentinel value. All you need to do is return a sentinel value. So none can be a sentinel value. You're absolutely right. But like if this is another programming language that has like, you're dealing with primitive types and it's maybe more strongly typed, that would be a problem. You would need to have, like, it's got to be an int, right? Unless you're dealing with objects, then it can be null or none, but it's a whole other thing.
Thank you.
Good question, though. Okay, there we go. Cool. Yeah? Great. So, let's think for a moment, okay? I have 3 students in here. Worst case scenario, how many times will this loop run? 3 times. If there's 100 students, how many times will this loop run? 100. If it's n students, how many times will it run? If it's 2n. Exactly. And the reason I say 2n is if I double it, it requires double the work, right? Work here is like how many times that loop is running. This is an example of a linear algorithm. Linear doesn't mean like, oh, it's n. Like, oh, it's going to run n times. Really, no, what linear means is that as you scale n up, the amount of work that you do scales linearly. There's a nuance there, but it's kind of outside the scope of this course. But it's important to be aware of these ideas. Point is, if the list of students gets bigger, this algorithm takes longer to run. Okay? So let's go down here and say like, okay, if I want to like print, find student grade, what was it called? My grades. And let's find Sally. Right there, cool. Right, it works. Wonderful. Now, oh, here I did it slightly different, where I did a linear search and returned the whole student, and then I just indexed it. Same difference, right? So assuming my grade was a dictionary, though, not a list of lists, but if my grades was a dictionary, like it was here, let's go here. If I want to know Sally's grade, there's no linear search. I just say, my grades at Sally. Oh, come on. Oh, what am I doing wrong? My grade. Oh, I didn't copy the right thing. Some dictionary. Okay, sure. But let's call it my grades. There. There. Now, there's no need for a linear search, right? Here, when I had a list of lists, where the individual internal lists were the students, I had to look at each one. But when I'm using a dictionary, it just looks it up. There's no call to a linear search here, right? Now, any questions before I move on to the next thing? Because the next thing is important. It's where the magic happens. I'll give you a second to think. All right, so if you remember last class, maybe it was the one before, when we talked about the sum function, right? Remember that one? If you call the sum function and you give it like a list, it'll sum up the contents of that list. And I told you, well, like, look, that's a function, but if you were to look under the hood of that function, you're going to find that that algorithm that we wrote to do the sum itself, where it's like, okay, for each number in the list, add it to a running total, right? So there's a loop in there. Meaning if we were to write that ourselves, there'd be a loop, and if there were 100 numbers in that list, how many times would that loop run to add all the numbers together? 100. If it was n, it would be n, right? 2n, it would have to run 2n times, right? So that's another linear algorithm. And then you might think, well, just call the sum function. There's no loop there. But there is. If you open up that sum function under the hood, there's a loop. Meaning you're not really actually winning. It's going to still grow linearly. The amount of work is the same. So you might think to yourself, is that what's going on here? Right? Sure, okay, we didn't have to do a linear search, which takes linear time. It's the loop's going to run each time for however many students there are. That's probably what the dictionary is doing. If I were to open up the hood and look under the code, at the code in the dictionary, there's like a linear search in there or something, right? No. What's crazy about this is no matter how, there's asterisks applied to what I'm saying right now, but in general, if this is a size 3, it's one lookup. If it's size 100, it's still one lookup. If it's size 1 billion, one lookup. If it's n, one lookup. If it's 2n, one lookup. It doesn't even matter how big it is. Where the linear search, the amount of times that loop had to run, the amount of work this code has to do grows the same way as the size of the input. Where this, no matter the size of the input, it takes a constant amount of time. Which is, by the way, wild. This is huge. This is a really big deal. If you've got one piece of code that's going to scale linearly, and one that's going to not scale at all, it stays constant time, you take this one. This is the right choice for something like this. But then, okay, if it's not doing a linear search, what the hell is it doing? It's got to somehow magically find what's going on. All of the details of how this works is outside the scope of this course. This is like second-year course level stuff, okay? But I'm going to give you an idea of how it works. And what it does is it makes use of a lot of space. It wastes space for the sake of like speed, all right? Like computational efficiency, which is a very common thing, right? They'll say like there's no free lunch, right? You win here, you lose here. Oh, maybe a little of this like this, right? So there's no free lunch. But how does this work? Well, if I have a list of size 100, the computer's going to go and block off a chunk of like 100 spots of RAM, right? Here's what's going to happen with the dictionary, actually. It's going to block off like a gigantic chunk of RAM, okay? Absolutely huge amount. Okay, it's hilariously large, pretend. Then what it does is it takes the key, all right, and by the way, it takes the key and it hashes it. I'll explain what that means in one moment, but I'll show you an error. Like, okay, if I could have a dictionary equals that, and I were to say, like, okay, if I can have a key that's like anything, can I have a key where it's like true equals false? I don't know. That's wild. Print my dict at true. False. It works. A lot of different types can go into what the keys are. But it has to be hashable. So if I were to instead be like, well, what if I gave it like a list? What if I gave it the list true? Right? Oh, I got it. What am I doing? What? Oh, here. It's going to say unhashable type. So there are limits on what you can use as a key. This is not on the test. Okay, I'm just letting you know, right? Now there's a solution. Tuples, on the other hand, are hashable. So you could actually use tuples instead. And that'll work just fine, but whatever. That's a nice quick solution to like, oh, I wanted a list and it's not hashable. We'll make it a tuple, it'll be fine. But anyways, it has to be hashable. So what does that mean? Well, imagine for a moment there is a magic function called h of x. All right? We'll call this a hash function. Okay? And often we'll talk about an idealized hash function, which doesn't exist, but we pretend really hard that it does. But an ideal hash function will take any key and turn it into a number. Some number. Okay? So maybe h of Sally maps to the number 422. I don't know. Right? Why? Don't worry about it. There's some magic hash function in here, I don't know. It magically converts the string to a number. And we want it, this is what makes it ideal. We want it such that every possible x will map to a different number. Okay? That's what makes it ideal. In reality, there doesn't exist one. You're going to have what we call collisions, where they map to the same thing, and then you have to deal with collisions. Don't worry about it. But if I put in like h of, who was the first one? Bob? Billy. Maybe that maps to 2. I don't know. And so on and so on and so on. So they magically turn these things to a number. And pretend like this is like 1, 2, 3. I said 422. 422, 423, 424. Arbitrary values, they don't matter, right? You can't see that, can you? But what we do is we say, okay, so in 422, we'll put Sally's grade, which was 88. 88. In number 2, we'll put Jimmy Bob's, or no, Billy's, 74, right? So that's how it would work. So then if you ever want to know, like, okay, that's how I store it. And then if I'm like, well, what was Sally's grade? I go, okay, pump it through the hash function, which runs like that. 422, oh, go look up 422. There you go. Now, there's a lot of wasted space in here. But with that wasted space, we get lookups that can happen like that. So no linear time algorithm anymore. That's huge. This is huge. But appreciating how amazing they are is not going to come probably in 161. Maybe 162, a little bit more. We could see, okay, wow, these really are valuable. But certainly in 255. They are a fairly advanced data structure. You can kind of see like how the magic happens, which is really cool. But there's a lot of other stuff going on under the hood, but this is the general idea. Any questions about that? It's pretty cool stuff. All right, okay. Okay, yeah. Why they're great? Okay, linear search. Here we don't need to. All right, remember how, and that was, okay, great, cool, there. All right, yeah. That's all I'm going to really say about dictionaries. I think you have to use a dictionary in assignment 4. I think that's it. Other than that, I don't think you're going to be using dictionaries much. So anyone have any other questions about dictionaries before I move on to sets? All right, sets. Who here knows what a set is? Who here has taken grade 10 math? I don't know. You know what a set is, right? What's a set? It's a collection of information, but usually sets are, the values have to be unique, right? You can't have like 2 of the same values in a set. Sets, it's like a group of unique values, unless you have what we call like a multi-set where you're allowed to have multiple versions of values. But typically a set is just a set of numbers, let's say, or a set of students, or a set of words, I don't know, right? So sets are pretty neat data structures. They are a niche data structure. There are a lot of very like niche data structures in that you're not going to use them very often, but when you use, but their utility is amazing when you need it. Okay? So you're like, these aren't a list, perfect general purpose data structure, you're using it all the time. A set, you won't use it very often. I don't think we even use it in this course at all. But when you need a set, they're awesome. They do the job perfectly, right? So it's a very niche one that has an amazing, it can do what it does really well, but it's not overly general purpose. And also, a funny little thing about sets too is technically they don't have an ordering. If I were to say, what's the first thing in a set? There isn't an answer. Python will kind of give it an ordering, but by definition, there's no ordering. So what are sets? Elements in a set are unique, but lists can have multiple copies. Yeah, sets also have no intrinsic ordering, but lists do, right? So like 0, right? You can index a list. You can't index a set. So here's a way to make a set, okay? Actually, you didn't even need to have the squiggles. That could have been square brackets, but whatever. Here is a set, all right? So here, let's just do that. I think if I just make it a list, it's also going to work. Yeah, that'll work. I wonder if I make it a tuple, will that also work? I imagine it will. Oh my goodness. Yeah, perfect, whatever. You just have some collection and you wrap it in the word set, it makes a set. There's our set, right? It's got squiggles. Dictionaries also used the squiggles. They're called braces. But what was different about a dictionary is it would always have like a key value pair, right? It would be like key colon value. This is just a bunch of information. That's all. So what's so special about what's going on here? Well, look, we've got Greg, Anna, Sally, Frank, Frank. I added Frank twice. When I made that set, there's only one Frank. Also, what's up with this ordering? How come it's Sally, Frank, Anna, Greg? That's not how I put them in. Yeah, it doesn't matter. It's just the ordering doesn't matter at all. The backbone of how these work are dictionaries, but yeah. Cool. See? Yeah? Happy? Sad? Neat. So what's so cool about them? Well, it allows you to use set operators. Oh, here's how you can add things, right? So let's say I've got this here, right? All right, cool. So these are students, let's say, that are taking 161 and other students that are taking Math 106. Anyone in here taking Math 106? Does Math 106 even exist? It does? Okay, cool. Perfect. All right, so there you go, right? We've got, 161 and 162, or 161 and 106. Cool, right? And we added Lynn here. Okay, cool, right? Yeah. Like, why was Lynn not appended to the end? Because it's a set and the ordering is whatever the hell it wants to be. So far, so good? I can do this. Add Lynn, add Lynn, add Lynn, add Lynn, add Lynn, add Lynn, add Lynn. And it doesn't change at all because Lynn's already there and sets can only have one copy of each thing. All right? Questions, thoughts, concerns, anything? Now, you can check if something exists in there with the in operator. Now, we're using in, which we've already used before in for loops, for thing in collection of things, right? But in is an operator that is context sensitive. In the same way that like plus acts differently if you're using it on numbers versus strings, in works differently, and I'll show you, right? I can say, well, because like I can't index these things, and maybe I could do like a linear search or something, whatever, but I could say like, okay, print Sally in Math 106, true. Okay, neat, I can do that. And again, because it turns out sets are built on top of dictionaries, this doesn't do a linear search. It's a constant time operation. It's always just going to look it up just like that. You could think of a set as a dictionary where the key is this, and the value associated with it is just arbitrary. It doesn't matter. It just basically checks, is the key there? Anyways. So you see? Yeah, in. Great. It tells you if it's there. Great. Is Ryan, and so we've got a Ryan and one. Okay, there's no Greg in Math 106. False. Cool. So it becomes really easy to check these things. All right? Without, like, again, this won't scale linearly. It's constant work, which is wonderful. Now, who here remembers set operations? It looks like you have a question.
I do.
What's up?
So I had like the set, like the CSCI 161 set.
Yep.
And I did print Greg in CSCI 161 and it gave me false. But I have the output of the print beforehand and it shows that Greg is in the set.
All right, well, let's try it. And I don't know. You've done something wrong.
I know, that's weird, isn't it?
I'm hearing a lot this year of like, yeah, I don't know. That's weird.
Right?
There's, if I were to dig deeper, there's definitely a problem. CSCI 161 set.
Oh my God.
It's because, see, it's not the same. Every time I have exactly what you have and it didn't work. You didn't.
So at least I didn't say that.
Yeah, that's true. You stopped yourself. He had this. So is Greg in there? No, Greg comma is. So yeah, remember, computers are assholes. It's going to do exactly what it's told. All right. Now, where is this going to come in handy? Well, if you remember from like grade 10 math or whenever you did this, I don't remember. But there are a couple of fancy operators that we can use on sets. Things like union, intersection, difference. All of these things provide us with a really cool way of answering questions. Like, for example, union is an operator that will give you a new set that contains everything from both sets. All right? And this is a Venn diagram. Who here passed grade 3? Perfect. So you should know what this is. Perfect, right? So that's what union is going to do. So it allows me to ask questions like, tell me all the students that are in 161 and 106. So I can say math 106.union. The order doesn't matter. CSCI 161. And there you go, right? There's all of them. And you're going to be like, well, Sally's in both. Yeah, but we don't like, these are all the students that are in both, right? Cool? Yeah? Yeah? Pretty neat, right? Neat. And yeah, the order doesn't matter. It's like that's the same thing. It doesn't matter if you do A union B or B union A, it's the same. Just like 1 plus 2 is the same as 2 plus 1. There's a name, there's a mathematical name for that. A property, what's it called? Associativity or commutative or which one is it? Come on, who's a math major in here? Yeah, that one? I'm going to hope you're right. Otherwise, we're going to sound like fools. But whatever. Cool. Union lets me know who's in, tell me all the students in both these classes. Intersection is another one where, again, the order doesn't matter. We'll tell you all the students that are taking both. Okay? So where before it was all the students in both, now it's tell me all the students that are in both. That is this part right here. That part of the Venn diagram, right? Where do they intersect? So who's in both? Well, Sally, Sally, Frank, Frank. Anna's not taking, no, and Greg's not over there. So yeah, there we go. Cool. Pretty cool, right? Intersection. And then, yeah, there you go, taking both courses. And then we have set difference. Set difference is a little funny, but like who's in B but not in A. And set difference, the order does matter, okay? So who's in B but not in A would be like this one, which would be different. Like imagine what this would look like if I said who's in A but not in B, okay? So that's set difference. So this allows you to say difference. Who's taking 161 but not taking 106? There, right? And these are common questions someone might want to ask. And you might say, okay, you could do that with lists and linear searches. Yes, but these are constant time. They go like that. And if you've got thousands and thousands and thousands of students, yeah, you don't want linear time algorithms. You want things that go like that. These are amazingly powerful. And the basic mathematical operations, like imagine like, okay, I want to do that. Okay, do a linear search. Are they in there? Okay, then do another linear search. They're in there, they're in there. If you have a function that says, give me the intersection, and you know what the math behind it, oh, I know exactly what that means. Who's taking both? Cool, right? I think that's pretty cool. But at this stage, you're probably thinking like, okay, yeah, that's cool, but hopefully you're getting an appreciation of what I mean when I say like, it's pretty niche, right? If I have a question of, hey, I want to know who's taking both classes, set's perfect for it. Perfect, absolutely perfect, right? But in general, you're not going to be using them very often. But when you need them, when you've got a situation where a set can work, they often are just like, oh, so good to use. Yeah.
So you use a set in a specific situation, and otherwise you use a list or a dictionary?
Trying to find a rule of thumb is a mistake. You use whatever makes sense for what you're doing, right? And you might have multiple options, and it might not be obvious why one's better than the other at certain times as well. All right, so like imagine I gave you all of the text from a book. Imagine like, oh yes. What if you have 3 classes? Well, then you could do, it's actually not too bad. So let's do like union. Let's say I've got like, what's another class someone's taking? Who's taking a physics class right now? And what's the code for it?
I think it's 121.
121, perfect. Equals a set, a new set, whatever. Actually, let's just do it like Greg, Sam, Billy Bob, George. Oop. And then, of course, Geoff as well, right? Obviously. Yeah. So there we go. Okay, we got Phys 101. So what if we want to know that? Well, you could just like kind of like chain them along. Dot union there. You could just chain them along. Or you can do it step by step, but well, why would it work chaining them? Well, consider the fact that 161 union 106 gives you a set. That evaluates to a set, which I want to union with another set. And I could do this with intersection as well. Set difference as well, but and that might get a little kind of weird to keep track of what is it actually doing. But like, I could do like, I want to know who's taking both 161 and 162 and everyone in 121, right? Yeah. Absolutely, you can. I would recommend doing it that way, where you could be like, okay, both 161, 106 equals CSCI 161 dot intersect math 106, right? And then you could do like, there, right? A lot of options, but yeah, fun questions nevertheless. So take your favorite book, all right? Take your favorite book. Imagine you can download it from the internet, and you can load it into a text file that you load into Python. So you basically have a giant text file that just contains every word, like the whole contents of your favorite book, okay? And if I were to ask you the question, what's the easiest way to count the number of unique words in that book? Throw it in a set, and then ask its size, right? Why would that work? Well, sets eliminate duplicates, so boom, there you go. Perfect use for a set. Count unique things, perfect. Sets, wonderful. What if I gave you another book and asked, which words do they have in common? Intersect, right? The number of unique words between both, intersect. What about the words in this book but not that book? Difference, right? So there are use cases for a set. And when they arise, they are perfect. Like one line of code to answer these questions, right? Phenomenal. Otherwise, you're doing like linear search for each word over there and then over there to there. It's a nightmare. This, perfect. Questions of other sets or anything? They're pretty cool. And we probably won't ever use them again for the rest of this class, but you know they exist. All right, who here has debugged before? We were joking yesterday in lab that when you're debugging, you are the detective that is tasked with solving the crime that you committed. So we've written a lot of algorithms so far, right? And you've gotten comfortable with Python, you're writing code, but how many of you have gotten a bug? Everybody, right? Some bugs are easy to spot, some are tricky. Some are like very silent, where they seem to be working most of the time, but they fail every once in a while. Debugging is challenging. And there's a lot of things we can do to hedge against having to debug later in how we build our code in the first place. Like do a very incremental approach. Write a few lines of code, did it work properly? Add a few more lines, did it work properly? Like that's going to help prevent bugs along the way. Because if you wrote like 50 lines of code, then you finally hit run and there's an error, you're like, crap. If you wrote 3 lines of code and you hit run and there's an error, well, chances are it's probably a little easier to find, right? So debugging. Having bugs in your code is normal. In spite of my warnings, I still hear students say like, oh man, it takes me forever. Yeah, debugging is programming. Remember that joke at the beginning of the semester I showed you, that hacker typer website? No one does that. That's insane. That's insane. Even though like every piece of media, when someone's programming, that's what they're doing, right? But that's not how it works. Your code's going to be wrong every single time you hit run before it's right. Remember that. And you're going to have to hit run a lot before it's right. That's the name of the game. Get used to it. At this, so raise your hand if you've had to debug your code before. Everyone put up your hand, right? So now, have you come up with like a strategy for your debugging? You just kind of willy-nilly just like, what about this? What about that? What about this? What about that? Right? Obviously you use like some insight of like, maybe it should have been 2, not 1. Like you're going to use some guesses. But has anyone come up with like a systematic strategy for debugging?
I wouldn't call it like high tech or anything, but usually what I do when I have a problem is, like if I have a lot of code and it's not working, I'll remove each part of the problem, run it, and then repeat. So like,
Until you find it, yeah.
Run it, repeat, and then eventually I'll find out where the problem is.
That's very good. Anyone else kind of try that strategy? Yeah, a little bit, yeah. Maybe a little this, a little that. What else have people tried? My favorite strategy is like usually when things are going wrong, it's because like the values are getting out of whack. They're not what I expect them to be or something, right? So what do? I just print out values. Like, okay, X should be 17 here, so print it out. 34, what, right? Like, so it helps you kind of find it. And often, like if you've got code, like if we go up, like let's say linear search, right? And you're like, okay, well, print student. It should be like I should get the student there, right? So if I run that, oh, negative. Why didn't that run? That doesn't make sense, right? So the point is, you can add prints, and often you're like, okay, well, if that didn't work, what if we put the print up here? Should that have worked? That should work. No, why did that not? You know, so there's like this. They call this like the REPL, the read, execute, print loop. Okay, programming languages that have like an easy REPL, like Python, really good. Make a change, hit run. It goes like that, right? Other languages, you make a change, you got to compile it. It's got to build. You got to wait, then you can run it. You make a change, you got to compile it. You got build system, and then you run it, right? Python, easy peasy, quick REPL for what we're doing. You make a change, you hit run, you see the difference. You make a change, you hit run, you see the difference. That's what you do. Sometimes, maybe you don't even have a value to print out. Sometimes you have like an if statement that should be triggering, right? It should be. So imagine you've got like, okay, this should be triggering. Right? Like, oh, okay, right? So like, do I see it? If I see it, then I know it triggered. If I don't, why did that if statement not go? So printing is going to be, it should be your tried and true low-tech mechanism for hunting down bugs. Print, 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 fantastic, okay? That's a good starting point. Now, okay, we're going to talk about a couple of popular debugging strategies. I'm sure whether you like it or not, everyone's kind of come up with their own little system. Maybe they're a little bit of what we're going to talk about, maybe not. But why do we have to debug? Well, because our code's wrong all the time. It's going to be wrong all the time. And as our code gets more and more complex, it's going to get more and more wrong more of the time. So no matter how good of a programmer you are, you could be the best programmer in the world, your code's going to be full of bugs all the time. It's the way it is. The types of bugs that you're going to encounter will change, right? An experienced Python programmer is probably not going to be making syntax errors as often as someone who's just starting out. Fine, fair enough. But debugging is going to keep haunting them. So, so beyond the obvious benefit of fixing your code, why is debugging important? Well, look. Here's why debugging is so... People come to office hours, let's say, and they're like, this code doesn't work. Help me. Okay, I'm happy to help you, right? But I really want to know, and that's why some of you who have come to office hours, I've asked them this question. Well, show me what you've done. What have you done? I want to see what they've tried. And this is why it's important. Again, I've said this before. I don't need you to give me stats on simulating a zombie apocalypse. I really don't actually need that information, okay? It's not that important. What I do need you to do is to build that code and do it. That's what I want you to do. The end result, great, cool. But I really don't need you to make me a tic-tac-toe game. I really don't. But I want you to build it. That's assignment 3, for example. I really don't need to know the density of Starbucks. But I want you to do it. It's that exercise of building, problem solving. That's what we're doing here. Getting the answer? I don't give a shit about the answer. It's all about how did we build the code that gets me the answer. That's the point. Think back in like math class, show your work. Why do you show your work? Because I actually don't give a shit about the answer. I care that you can get the answer. That's the point. So, I need to know that you are debugging. Why? Because debugging is programming. And in order to be good at debugging, you have to have a good understanding of what the hell you're doing. You got to understand the problem. You got to understand your strategy. You have to understand your programming language. You have to be able to think through this systematically and logically, and you can follow and flow of your code, okay? Those are all skills you need to develop, and you're going to develop them by beating your head against that keyboard for as long as it takes. That's how you learn this stuff. I'm a broken record, but it's the way it is. Is there a better way? No, not that I know of. So, get used to it. I want you to feel the pain of debugging because that's how you get to the other side. Anyways, have a great weekend. And I'll see half of you in like an hour, right?